Okay, today we're going to talk about chemical equilibrium. Yes. Um, Essentially what it is it's a concept where we study chemical reactions that do not go to completion. And what the heck does that mean? Well, I guess we can start out with some basic chemical reactions that you might learn when you're first starting chemistry, how to write equations, how to write balanced equations. So in this particular case, we've got HCl plus NaOH, that's an acid and a base, and that goes to NaCl, which is a salt and water. And that is perfectly balanced, as we can see. With this one, this is CH4 plus O2. This would be combusting a hydrocarbon, presumably in open air with oxygen, burning methane, CH4, specifically this time around. And it produces CO2, which is carbon dioxide, and H2O. So what we've got here is 1C, 1C, 4 H's, 2 H's, and so I'll have to throw a 2 in front of there so that we got 2 H2's. That's going to be 4 H's to balance the 4 H's, but in doing so, I've got 2 oxygens on the water molecule and 2 oxygens on the carbon dioxide. So I'll have to throw a 2 in front of there to balance that. So these are things that hopefully you will have seen already by the time you get to the concept of chemical equilibrium. But with these basic equations, it's kind of, in the most simplified fashion to present this. You're basically taking the things on the left side, which are considered the reactants that you're starting out with. You're mixing them together either in a beaker, in a liquid, in a cylinder of some sort, if they happen to be a gas, or you can combust them in open air. So essentially whatever method you need to conduct to chemically react these things, you do that. And it's thought that when these reactants mix together, some period of time goes by. It might be a fraction of a second, or it might be 10 minutes or a half an hour, but in any event, you start out with your reactants, you mix them together, you let them do their thing, and then you come back, and then at some point later, the reactants have turned into products. So the reactants are now gone, and you have products, right? So those reactions are thought to go to completion, so to speak. But the concept of chemical equilibrium, and I'll give you an example here. Let's see, might as well balance this right from the very start. So the concept of chemical equilibrium addresses a reaction like this where maybe this reaction would take place in a closed 1 liter chamber, and the reactants H2 and I2 would be injected into the 1 liter chamber, and at some point later it will produce HI. And in a balanced fashion, 2 H's from the H2 and 2 I's from the I2 will produce 2 HI's, so that you get 2 moles of HI comparatively. And these would all be gases, both start to finish, when they're in this 1 liter chamber that they're injected into. So with a balanced equation, if this were a perfect world and all chemical reactions everywhere went to completion, then that would mean if we had 1 mole of this injected into the chamber and 1 mole of this injected into the chamber, we could come back at some point later and find exactly 2 moles of HI, because that's the product that would be produced. But in this reaction, for example, we come back after it's reacted, and we find that we have 0.21 moles of the H2 left unreacted, 0.21 moles of the I2 left unreacted, and we have 1.58 moles of the HI actually present in the 1 liter chamber. So they have reached a chemical equilibrium, meaning that we could wait another hour or another day and it's not going to go any further. It's not going to take any more of this leftover H2 and I2 and finish the job, so to speak, and produce 2 moles of HI. We're going to be kind of stuck at 1.58. And I should say that all chemical reactions are based on conditions, and the numbers that we get with this are actually based on around 430 degrees Celsius in this case, in this 1 liter closed chamber. If we were to change the conditions, we might change our distribution, our ratio of reactants to products. But it begs the question, if you're first starting out learning this, what exactly is happening? I mean, these react, they go to completion, you're done, mission accomplished. In this case, you've produced some product. As a matter of fact, a majority of it is converted to product. But out of that 1 mole, we've got about 0.21 moles left over of each thing. So does it just go up to a certain point and then the H2s and the I2s get tired and say, oh, I'm not going to react anymore, and they just stop? What's happening? And by the way, why do they stop at 1.58, which is around 80% of the entire 2 moles if it were to go to completion? So why doesn't it go to 100%? Why doesn't it stop at 30? How did it magically arrive at 80? And the answer is that the concept of chemical equilibrium actually deals with the fact that in this particular environment, conditions are favorable so that H2s and I2s can chemically react, their bonds can break, and they will form HI molecules. So an H2 and an I2, the original bonds can break, the new bonds can reform, and you can produce these little HI molecules that are now floating around. But what they've discovered is in this same set of conditions, a closed 1 liter chamber at 430 degrees Celsius, there also exists the possibility that some of those HI bonds can break and reform back into H2 and I2. These reactions are running simultaneously. So it's almost like there are 2 reactions now taking place in this chamber that are almost independent of one another. Because the H2s and the I2s, it's favorable for those bonds to break and produce the HI, and it's now favorable for the HI bonds, some of them, to break and form back into the H2 and I2. So that's why we have the double arrows here going in each direction, because in this chamber, while it's just sitting there at 1.58, it's not like it's done and it's come to a complete stop. There is actually a reaction running forward and running in reverse simultaneously. Interesting to note that because we've produced 1.58 moles, or in this case about 80% of our possible product, then it means at least we've produced a majority of the product, and only a small amount is in the H2 and I2 state at any given time once it hits equilibrium. And one way to understand that properly is I'll use a dart gun example. If I had a whole mess of darts on the floor here in this room, and I decided I'm going to load some darts into my dart gun and shoot them up at the ceiling and hope that they stick to the ceiling, in the amount of time that I can shoot 20 darts, and I'm going to go as fast as I can, shoot 20 darts up at the ceiling, then I'll say maybe about 10% of the darts that are sticking to the ceiling, the adhesive will kind of wear off and they'll become unstuck. Okay. So when I shoot up my first 20 or 30 darts, the amount going up is way more than the amount coming down, because in the very beginning I've only got my first 20 up in the ceiling. So 10% of 20 is only going to be 2 darts. So in the very beginning, the amount going up is going to far outweigh the amount coming down. But as time progresses, and let's say I've got somewhere around 200, 220, 240 darts, somewhere in that neighborhood, as time progresses, as I'm making inroads and making headway, and the amount of darts I'm shooting up just accumulates, and I've gotten more and more stuck to the ceiling, I'll get to a point where I've got 200 darts stuck to the ceiling, and I've got just a few darts left down here on the ground, and I'm furiously shooting them up 20 at a time. But when I get to the point where I've got 20 up on the ceiling, then 200. When I get to the point where I've got 200 up on the ceiling, then 10% of 200 is 20. So in the time that I shoot that next batch of 20 up at the ceiling, exactly 20 are falling down. So if my hope was for every single one of these darts on the floor to stick to the ceiling, stay stuck to the ceiling, so I could walk away at some point later and say, when I started, all the darts were on the floor, and when I finish, all the darts are on the ceiling now, I'll never get to that end point because I will eventually get to a point where the amount of darts falling will equal the amount of darts going up, and I will hit a quote-unquote equilibrium point. So I'll never get past that point, unfortunately. And when I hit that equilibrium point, I can actually count the amount of darts I've got left over on the floor and compare them to the amount of darts on the ceiling to, at the very least, see how successfully I could get those darts up on the ceiling and what percentage of those darts I could get to stick. Now we could change the conditions, right? I could make the darts a little less sticky so that at any one given time 50% of the darts fall or 80% of the darts. So I may still get a few straggler darts that are going to be sticking up there, but I'm going to hit equilibrium a lot sooner, and it's going to be a less successful dart reaction, so to speak, because with the other case, I got to around 200. So I almost hit the end, right? But I did fall short, but I got to about 200. In the next example, because I've maybe changed the condition of the adhesiveness of the dart, the best I might be able to do is maybe 40 or 45 darts, but as I keep shooting, more darts are going to come down more quickly. I could also maybe put add a little bit of adhesive to the dart so that maybe 99% of them stick, and only an occasional dart falls down here and there. So I can be talking about different chemical reactions, I can be talking about different conditions for those chemical reactions, and I can track how successfully forward that reaction runs, or how much product I can produce versus how much reactant I have left over. And if it's a very successful reaction going forward, then I will find that a vast majority of the reactant will have turned into product by the time I hit my equilibrium point. And if it's not a very successful reaction in the forward direction, then what that means is the conditions are a lot more favorable for those product bonds to re-break and reform back into the original reactant. So again, we've got two reactions going on simultaneously, and in this case, it's more favorable for the H2 and the I2 bonds to break and form into HI. And even though conditions are favorable for some of the HI to re-break and form back into the original H2 and I2, it's not as mathematically likely at any one given time under these conditions. So then you say, well, if it's not as mathematically likely for this to go into this, how and why do we hit that equilibrium point? Well, because even though the HI bonds re-breaking to form back into the H2 and the I2 is less mathematically likely from a probability standpoint, I guess we could say, what makes up for that is, again, at some point, we will hit sheer numbers of HI that at some point we just build up a higher and higher and higher quantity of HI, and meanwhile our original quantity of 1 mole of each of these guys will dwindle and dwindle and dwindle till we get to the point where the raw numbers of this being much more than what we've got over here will compensate for the fact that it's more likely to run forward than it is to run in reverse, right? So again, the likelihood of the darts falling at any one given time isn't as likely as me having the ability to shoot them up there real fast, but once we get the raw numbers of the darts up at the ceiling, something that on an individual basis and probability-wise that is less likely is compensated for because we actually have more of them up there to compensate for the fact that it's less likely. And then the pure mathematical amount of darts falling will then be able to equal the amount of darts that I'm shooting at. Okay? So how do we track the exact success rate of these reactions? Well, what's being tracked here is the amount of product produced, obviously, versus the amount of original reactant left over. And chemists actually make a fraction out of it. So they put the products, the concentration of the products when we hit equilibrium up on top, and the concentration left over, of how much is left over, of the reactants on the bottom. So when this fraction is divided out, you can see that the more successfully forward a reaction runs, or the more product we're actually able to produce, then we're going to have a higher number up here, and most or all of this, well, most or a vast quantity of this will disappear or dwindle down to a small amount. So for successful reactions, needless to say, we're going to have high numbers up here, low numbers up here, and that's going to give us a high fraction of some sort, generally above 1. But if we have a reaction that is quote-unquote an equilibrium reaction, because it's running both ways at some point simultaneously, but it's not very successfully forward, then that means the mathematical likelihood is actually better for, the conditions are better for the reverse to take place than it is for the forward. Again, they'll both run, but because the likelihood is much better, more favorable to run in reverse, then that means, and I'll give you a reaction, for example. So here's a different reaction. Here's 2 moles of NaCl, and it's going to convert to 2, these are all gases, and it's going to convert to 2 moles of NO and a mole of Cl2. And we have a much lower likelihood or probability of these NaCls turning into these products and staying that way, so to speak. So if we go back and look at this reaction at some point later under certain conditions, we'll find that our concentration of the products comparatively are much lower than the original reactant that's left over. So we're going to have a very unsuccessful reaction here compared to this one. This was pretty decent. So if we were to compare both of these reactions and say, well, geez, I've got a whole bunch of chemical reactions, and I want to rank the ones that are pretty successful in the forward direction, and maybe put on the bottom of the list some of the reactions that are not very successful going forward, and they might only produce very small trace amounts turning into product before it hits equilibrium, then we're going to plug the relative concentrations into this fraction, and again, the more successful that our reaction is, when this fraction is divided out, the higher the number, and obviously the more unsuccessful the reaction is at maintaining forward and producing products, then when this fraction is divided out, it's going to give us obviously a low result when divided out. Seems very simple, and it's not quite as simple as that, because there's some rules and regulations for how we plug the concentrations of the products and reactants into the fraction. So that's the potential bad news. The potential bad news is that it's not quite that simple, but it's almost that simple. So what we've got is, and I'm going to go back to this H2 and I2 reaction with the 2HI, at equilibrium, which by the way, when these fractions are divided out, we log what the actual numerical value is of the result of those fractions divided out, and we get what's called an equilibrium constant value that's unique to that chemical reaction under those particular conditions. So we would get a equilibrium constant K value, sometimes it's called a KE, sometimes it's called a KC. I'll go with KC at this point. And for a reaction like this, we have the concentration of, in this case, HI on the top of the fraction because it's a product, and we've got the concentrations of H2 and I2 down here. And that's going to equal some sort of K value, all right? Almost that simple. The rule is, if I'm mixing together some reactants and products, A and B, to get C, and I've got X amount of A and Y amount of B produces, should remember to plan ahead, Z amount of C. So those are our coefficients. In a balanced equation, we'd have X amount of A, Y amount of B, and Z amount of C. in our what's called mass action equation, or chemical equilibrium fraction that we're going to produce for the concentrations, that's going to convert to C being our, in this case, our product up on top, and A and B being our reactants down here. What you do is, whatever the value is of the coefficients, x, y, and z, those would actually be taken to the same exponents when put into the fraction. So in this case, if I've got just 1 mole of H2 and 1 mole of I2, producing 2 moles of HI, then over here, this is just going to be H2 to the 1, so we'll just leave that as H2. I2 to the 1, leave that as we won't write the 1. But because we're producing 2 moles of HI, that HI concentration, whatever it is, will be taken to the second power, all right? And when all of these are divided out, as long as we're talking about the same reaction in the same conditions, they will equal some fixed K value. So that's the nice thing about this, is you do have to be mindful of your exponents as they relate to your coefficients. But once you use that in the math formula, you will have a K value that you can always count on for that, and that will be a very powerful tool when you're trying to find out unknowns with regard to any chemical reaction that's at equilibrium. So with this case, the H2 and the I2 going to 2 moles of HI at 430 degrees Celsius, that K value, the result of that fraction when divided out, will give us a number of around 57, okay? So what can we do with that 57? Well, quite a bit, actually. Because if, for example, I'll get rid of these. If, for example, we had some known quantities and those known quantities were at equilibrium, we have, say, 0.3, down here we had 0.2, 0.2, and 1.5 up, but let's say we change the numbers. Let's say that at equilibrium, we know that we have 0.3 moles of H2 and 0.3 moles of I2, and we know that we're going to wind up with a number of 57. That's something that we can count on because that's the actual textbook value of this reaction under those conditions. And we say, well, geez, if we are able to measure 0.3 moles of each of these guys at equilibrium, how many moles of HI will we have floating around in that container at equilibrium? And a word of caution. When we're solving these problems, I mentioned a moment ago that the fraction is representative of the relative concentrations of the reactants and the products. So I'm kind of carelessly jumping back and forth between moles and concentrations, which would be molar. The reason why I can do that in this case is because the example that I gave was a 1 liter chamber. So if I'm injecting these into a 1 liter chamber, then having mole quantities, raw numbers of each one of these species, would also give me molar concentration quantities. So in a 1 liter chamber, having 0.3 moles of this guy and 0.3 moles of this guy, I would also be able to say that my concentration is 0.3 molar because it's a 1 liter chamber. Obviously, if I started out in the language of moles, but I was talking about a 2 liter chamber, then my concentration would be half of that molar value because I'd be dealing with a larger container, right? So in this case, I'm going to keep it to a 1 liter chamber so I can freely go back and forth between moles and molar concentration without having to change my numbers. But make no mistake, when you're running the math here, in order for this to work out, it's dependent on the true concentration values, and if you have a case where they are different than the raw number of moles, it's the concentration values that must be plugged into this equation in order for this to work, okay? So this is what we've got. We've got an unknown quantity of HI at equilibrium. but we have a known quantity of the two reactants, and we know that this whole thing is going to come out to be 57. So if I do a little math here, and I say, well, 0.3 times 0.3 is going to be 0.09, and that's going to equal my HI, whatever that is, squared, and then that's going to equal 57. Then I could multiply both sides by 0.09, and then I've got 0.09 times 57 is going to equal HI squared. So let me run some numbers here. .09 times 57 is going to equal 5.1, and that's going to equal HI, whatever that concentration is, but squared. So obviously to isolate the unknown concentration of HI, we'll take the square root of both sides, and the square root of 5.1 is going to equal 2.265. I make no claims on accuracy of significant digits. Purpose of this is to conceptually help you understand chemical equilibrium. So sometimes I might get a little crazy with my digits, add one on, take one off. So make sure you're good with significant figures, because this isn't the place to learn that. Anyway, so we've got I'll just say 2.26. So by taking the square root, that is going to be our concentration of HI at equilibrium. So it's a nice tool. The concept of chemical equilibrium can basically, if it provides a K value for a particular reaction, and there are some of the pieces of the puzzle missing at equilibrium, namely one or more of the concentrations of the reactants or products at equilibrium, it actually allows you to solve so that you can have an expectation of how much, in this case, HI, you will have present, both in this case, how many raw moles of HI we have present, and what our molar concentration is of HI at equilibrium. So like a typical algebra problem with something known, we can solve for the unknown thanks to this, what's called mass action expression or equilibrium equation. All right, so that's that. And again, if we were to plug this 2.26 back in here, re-square this, and then divide it out by everything down here, it's going to come out to be approximately 57, depending on how well I did with my significant figures. Right? All right, so let's look at the next level here. We'll stay with the H2 and the I2, converting to 2HI, and we'll say that we still have a 1 liter chamber. And so our conditions are the same, so that our K value for this reaction will stay at around 57. But in this case, we have a question where we say we inject 0.2 moles of H2 and 0.2 moles of I2 into this 1 liter chamber, allow them to react, and we want to know what is the concentration of all three of these things once it hits equilibrium. So the reason why this one's a little more difficult, as you might be able to guess, is we don't know what any of the concentrations are at equilibrium. The last one, at least, we knew what the concentration left over of the reactants were, and we were able to quickly figure out the only unknown, which is the HI. But in this case, we only have starting concentrations, which really means nothing, because it doesn't tell us what any of the concentrations are at equilibrium. So if we're injecting 0.2 moles of H2 and 0.2 moles of I2, what are our concentrations going to be? We can make a table. We can say the more we know about this, the better. So before equilibrium, meaning initially, what are our concentrations? we can say that we don't have any HI because the reaction starting, so our HI quantity is 0, right? And before the reaction even starts, the amount that we're ejecting of H2 and I2 is the 0.2 moles and the 0.2 moles. At equilibrium is now the unknown for all three. But we can turn it into an algebra problem because the amount of H2 we lose when it converts over, same with the amount of I2, will contribute to how much HI we produce, right? So for example, if I have 1 molecule of H2 and 1 molecule of I2, and that produces 2 molecules of HI, keep that ratio in mind because we could use that with any number. I could say that I've got 100,000 molecules of this and 100,000 molecules of this, and that will, if it were to go to completion, produce 200,000 molecules of that. Well, the fact that it's an equilibrium problem and at any one given time only a fraction of it is successfully turning into product rather than the entire thing, we can still take advantage of that. Because whatever amount successfully converts over, it'll still convert over on the same ratio. So if I start out with 100 molecules of these, 100 molecules of these, and only, 80 out of those 100 convert over. So if I lose 80, and I lose 80 of these lost and 80 of these lost will still produce 160 of these, right? Because whatever amount of H's I've got, and whatever amount of I's I've got, let's say that these are the amounts that are going to be lost. So when I break these bonds here and break these bonds here, I'm losing 2 of these that will successfully convert over, and I'm losing 2 of these that will successfully convert over. And what that will do is produce 1, 2, 3, 4 loose H's, and 1, 2, 3, 4 loose I's that will then recombine to form HI. So I will have a quantity of 4 HI's when all is said and done from the amount of H that I lost and the amount of I that I lost, right? So the important thing about that concept is I don't know how much I have at equilibrium, but at least I know that I have 0.2 moles, which was my initial amount, minus how much I lost, which I can just call X, right? And I can say that the amount of I2 that I have at equilibrium would be however much I started with, the 0.2 moles, and it kind of could be 0.20 or 0.200, but we'll just keep it that, minus how much that I've lost. So, right? So if I have 100 molecules of each of these guys, and I successfully lose 80, then I'd have 20 left over. 100 to start with, I've lost 80, how much have I got left? 20. Same thing here. We just don't know how much we've lost. So we're phrasing it in terms of X. 0.2 moles to start with, minus some unknown amount. 0.2 moles to start with, minus some unknown amount. But then we go to our concept down here that says, hey, whether we know how much we've lost or we don't know, one thing we can count on is the ratio of what's lost of each of these guys turns into twice the amount of what's gained for these guys. So at equilibrium, I'm going to wind up with 2x amount of HI, all right? I think my eraser's hitting equilibrium with the board. Okay, so let's set up our fraction. We don't know any of these things. So our products, which is 2x, which will represent our, at this point, unknown concentration of HI, because that's a coefficient of 2, even though we've got 2x for a concentration representative, they would still be taken to the second power. So we've got to remember this 2 because of our algebraic showing the proper ratio here, and then the rules of this particular equilibrium equation, which will show that it's taken to the second power. So it's, remember both 2's there, one for the amount and one for the exponent. And what's our concentration of H2 and I2? Well, our concentration of H2 is 0.2 moles minus X, And this is also 0.2 moles minus x. Right? And that all equals 57. So what do we do with that? Well, what we can do is use algebra to the best of your ability and to really maximize your ability to do these problems, because once it becomes a pure algebra problem, that really what takes over. I mean, it starts out as conceptually as a chemical problem. I'm dealing with equilibrium. We're going this way, we're going this way at the same time. But at some point you can illustrate it purely as a math problem, and at that point, if you're decent with algebra, it should solve itself. What we notice here is this is a squared value up here, and these two are identical. So we could rewrite this as 0.2 minus x squared. And then what we have is, if we have this squared over this squared, we could basically say that the entire fraction is squared. So this whole thing would be squared. And then to make some headway with this, we could take the square root of the whole thing. So if we take the square root of the whole thing, we're taking the square root of 57. We're taking the square root of this whole thing, which is going to wipe out that guy. And then what we're going to have is, and we took the square root of 57 before, so that's still going to be 1.51. We're going to have 2x over 0.2 minus x, and that's going to equal 7.55. Yeah, I jumped the gun, I said 1.51, we're not there yet. So the square root of 57 is actually 7.55. Taking the square root of both sides, this is what we're left with. Then what we could do is we could bring this over and say that 7.55 times 0.2 minus x, and then multiply this side by 0.2 minus x. We're multiplying both sides by 0.2. That's going to wipe that out. And then we're going to say that 2x equals 7.55 times that. We distribute that in, and the 7.55 times the 0.2, that's where we're going to get our 1.51. So we're going to say that 2x equals 1.51 minus 7.55x. Because we're going to distribute that into both, and then we wind up with this. And now we're getting closer, because what we can do is we can isolate and solve for x by subtracting the 1.51. Well, what do we do here? We'll subtract these, well, we'll add the 7.55. We'll get it. We'll add the 7.55x to both sides. For those of you playing along at home, you've already figured this out. So then what that's going to produce is, haven't had my coffee yet, because I don't drink it. That's going to add these two x values together, which is going to be 9.55x. That's going to wipe that out, and we're just going to say that 9.55x equals 1.51. All right. Now we can solve by dividing both sides by 9.55. And when we divide both sides by 9.55, 1.51 divided by 9.55, x is going to equal 0.158. X equals 0.158. Give or take a significant digit here or there. All right. Now, what does that do for us? Well, that actually allows us to solve for all three at equilibrium. Why? Because we were able to phrase all three of these unknown values, unknown concentrations at equilibrium in terms of x. So now we can say 0.2 minus some amount that we lost will give us, after all said and done, will give us our value at equilibrium. Same thing with this guy, and the amount of HI we produced will be twice the amount of the X that we lost. So all we have to do now is just plug these numbers in, and what we get is the 0.2 minus the 0.158 at equilibrium will actually give us 0.042 moles or moles per liter by keeping in concentration, which we should be doing. Our I2 would be the same thing, 0.042 moles per liter. And then our amount of HI that we produce would be twice that, which is just going to be 0.316. So this K-value concept, this mass action equation, the concentration of the products taken to their appropriate exponents over the reactants, is a very powerful tool because it actually allows us to take something with no known quantities at equilibrium and solve for all of them so that we can now go back and say, okay, with the information that we were given, the amount that we inject initially, we know we can come back later and see that we will have produced 0.316 moles per liter of HI with a leftover amount of 0.042 moles of H2 and 0.042 moles or moles per liter of I2 at equilibrium. So it works that way, right? I'm going to do another one. Okay, we're back. Board's a little cleaner, my arm's a little sore. Did everything I could to get this stuff off, but I'm accumulating more marker residue than I can handle. So, switching gears here, we now have H2 and F2, because we can't mess with iodine all day long, we'll get bored. So we got H2 and F2 going to HF. Again, they're all gases in a chamber. And in this case, because we have a different reaction, we have a different K value. That 57 was unique to the H2 and I2 producing hydrogen iodide, but because we have a different set of reactants, we have an expectedly different success rate. And in this case, looks like it's going to be more successful because our K value is not 57, it's something much higher, which is around 115, right? But what's going to make this problem different is, up until this point, we've been dealing with problems where the amount of actual reactants that we're using in a laboratory, if we're injecting molar quantities into a 1 liter chamber, it is actually the proper ratio to produce whatever product that we're expecting. So before we had a 1 mole to 1 mole ratio to produce 2 moles, and we always had equal quantities to start with of the H2 and I2. But sometimes you're just stuck with what's given to you. You know, you might have, okay, I'm going to react an amount of H2 with an amount of F2, and I'm just going to mix them together, but they might not be equal quantities. So in this case, what I might have to work with is an initial amount of 1 mole of H2 and 2 moles of F2. So I've got a mismatch because on a balanced equation, 1 plus 1 will give us 2, but I've got an excess of F2 or considerably a shortage of H2. So when I mix those together, conceptually I might be a little, I might not know where that's going to bring me. But again, the great thing about this mass action expression is once you know how to do it properly, setting it up to equal the K value, and being mindful of all of the coefficients that will have to turn into the appropriate exponents in that equation. If you follow all those rules, that will solve your problem whether you've got a mismatch or not. Essentially, you could start out with any quantity of reactants and or products that you're initially sending in, and even if they are anywhere near what the balanced equation should illustrate, that equation will take all that into consideration, so that when you solve for x and therefore solve for what you should land with at equilibrium, it will make those adjustments and tell you what your equilibrium amounts are anyway. So that's the great thing about this. So kind of piggybacking on what we had last time, if this is before equilibrium, then our amount of H2 is going to be 1 molar or 1 mole. Our amount of F2 is going to be 2 molar. That's an M, wow. And then our amount of HF is going to be 0, because the reaction hasn't started yet. These are initial conditions, right? We come back at some point later, and the amount of H2 that we have is going to be the 1 mole that we started with, or 1 molar, minus some amount that did successfully convert over, which again, we don't know how much that is. We know it's going to be pretty decent because we've got a K value of 115, but we'll figure that out when we get there. So let's say we got 1.00 minus the amount that we lose will then give us our remaining amount at equilibrium, which is what we're looking to solve. So again, if the question is posed, well, if we inject an initial amount of 1 mole of this and 2 moles of that into the 1 liter chamber, how much of all of these things will we have at equilibrium? So it's essentially very similar to the last problem, with the exception that we have a mismatch here. And then over here we have 2 moles minus the amount that we lose. And then, like the last problem, since 1 and 1 will give us 2 in a balanced fashion, we can at least count on that the amount of HF that we do produce will correspond with twice the amount that we lose for each one. By the way, it's a 2-to-1 ratio. So this is, when you're choosing your algebra here, do it in a way that's going to be most convenient. Because you could say, well, hey, I'm starting out with 0 HF, so I could say the amount of HF that I produce, I could call that X. Well then, right, but if you know that it's going to be twice the amount that you're losing over here, then if you call this guy X, then the amounts that you're losing over here is going to be 0.5X for each. Bigger headache than keeping your lowest X value at exactly 1. So we have an X we're losing here, an X we're losing here, and a 2X that we're gaining there, right? So to set this up, what we're going to have is, let me do this down here. 2x, which is our unknown product value, squared, over our somewhat known or hypothesized reactant value for each, which is going to be the 1 minus x that we lose, and then the 2 moles minus the x that we lose of that guy, right? And that's all going to equal approximately 115. And we don't have the same values here. So what's different about this compared to the last one is we're not going to say that this value is going to be squared and we can just consider the whole thing squared and just take the square root. Since we have a mismatch here, then what the way around that is our next our plan B for something like that algebraically would be to FOIL this on the bottom. So if we FOIL this on the bottom, and then we by the way, when we have this squared value that's not going anywhere, again, in the last one we had squares up on the top and the bottom, and we just simplified and made the whole thing squared and took the square root and got rid of the square value. The two things that make this different are these two numbers are different, so we're going to have to FOIL these, and then the other thing is that this square value isn't going anywhere, so we have to deal with it. So when we're distributing our squared value in, it goes into both pieces of the bracket. So really what we wind up getting is 2x bracketed squared is going to wind up being 4x squared, right? So we'll replace that with 4x squared. And down here, if I FOIL these two guys, then that's going to give me x squared minus 3x plus 2. And that all equals 115. So what we could do is we could multiply both sides by this whole guy, and that's going to give us 115 x squared minus 3x plus 2. We distribute the 115 in. Again, multiplying both sides is going to get rid of this, so that we can then say that 4x squared equals all of that. And now we're getting closer to having a pure algebra problem, because 4x squared will equal 115 x squared minus, what is that, 345x? Plus 230, right? And then what can we do? We can then subtract the 4x squared from both sides, because we got like terms here, and by subtracting 4x squared from both sides, that's going to convert that guy to, well, 115x squared minus a 4x squared is going to leave us with a 111x squared. And since we subtract that from both sides, we're basically going to say that this whole thing equals 0, and when we have an x squared term and an x term and a numerical term all set equal to 0, we have the format of ax squared, in this case minus bx plus c equals 0, and so when we have ABC in that format, then we know that the quadratic is coming to solve for that, but at least we will be able to solve for that. So if we run all of that through the quadratic, which is, I'm not going to write that out, but again, our A value is 111, our B value is 345, and our C value is, negative 345 actually, and our C value is 230. When we run that into the negative b plus or minus the square root of b squared minus 4ac all over 2a, we wind up with two x values, because it's a quadratic, and that's what you get. X value number 1 is going to be 0.968, and x value number 2 is going to be 2.14, right? But one of these is going to be nonsensical. And you can imagine that it's going to have to be this one that we're going to omit, because you know, a quantity of 2 minus the amount that you're losing is going to have some amount left over. You can't lose more than what you start with unless you have a credit card. But in chemistry reactions, there are no credit cards. If you have 2 moles of something in a container, you can't come back and say, wow, I had 2 moles and 2.14 moles disappeared. So that allows us to say that our x value equals 0.968. And then after that, we just simply plug in, and our H2 value is going to be 0.032. Our F2 value is going to be 1.032. And our HF at equilibrium is going to be double this amount, because it's just going to be 2x. There was none to start with, and everything that was produced is now our amount of HF that we have, which is going to be 1.936. And again, because we're in a 1 liter container, we can simultaneously say that this is our raw number of moles for each, but we can also say, more importantly, because that's what the math is telling us, that our molar concentrations of these 3 things at equilibrium is 0.032 of that, 1.032 of that, and 1.936 of that, and that's what we have at equilibrium. So we had a knowledge of none of them, and now we know all 3 thanks to the power of this equation. And again, to check it, we could plug all these back into our equation, and when taken to the proper exponents and divided out properly. And it's important to remember that you know, this is still going to have to be taken to the squared power, and everything else is going to have to be plugged in and multiplied together. And if you get, you know, 115, 114, 113.9, somewhere around there, to check, you know that we're on the right track and we did this correctly. So these are our molar concentrations at equilibrium. And again, what does that tell us? that tells us that even if we put in a mismatch, an unbalanced amount, so to speak, and put in an excess of this or a shortage of this or whatever, we can still figure out where everything's going to land at equilibrium, because it's all going to be true to the fraction that divides out to give us our known K value for that reaction under those given conditions. So chemistry is not only a wonderful thing, but the algebra that you use to solve it is also, right? Shall we do another? I guess. Promise this is the last one. Then we can take a lunch break. And the reason why I'm doing this one is because this is something to watch out for so that you can make life easy for yourself. I had mentioned much earlier that we had a reaction that was 2NoCl, and that went to 2NO, and that went to Cl2. And I said that that was compared to the first one that we looked at, which was the hydrogen and iodine going to hydrogen iodide gas, that this was far less successful at maintaining the products going in the forward direction. And we said that the amount of HI produced corresponded with a K value of 57, which was pretty successful because it was far above 1 when that fraction was divided out. In this particular case, this is so unsuccessful that this gives us a K value of 1.6 times 10 to the negative 5. So when we divide out our fraction, after we divide out our fraction, that's going to be the result of our fraction divided out. So we can really imagine an enormous amount of reactant staying in the reactant phase, and only a small amount of product being successfully produced by the time we hit equilibrium. Again, that would be if I had darts that were almost Teflon, and they barely stuck to the ceiling, and maybe only for a fraction of a second. At any one given time, somebody walking by the room would only see a few darts stuck to the ceiling because they're going to fall down pretty fast. So a majority of my darts will always be on ground level, and they'll be running back and forth, but the amount that, if you look at the ceiling, the amount are actually stuck to the ceiling for any one given time. If you were to take a snapshot or a photo of that ceiling at any point in the proceeding, once we've hit equilibrium, it will be a very, very small fraction of darts, because of now we're talking about a reaction where the conditions are different. In this case, we're talking about a whole different set of reactants and products, and the energetic favorability under these conditions far favors these guys converting back into this, and it doesn't produce a very high mathematical likelihood at all that these will successfully turn into these. Some of it happens, but just a tiny, tiny amount. So because it is technically an equilibrium reaction that will produce some concentrations, as poor as they are, we can figure that out. So if our K value is 1.6 times 10 to the negative 5, and that equals our reactants, which is our NoCl concentration, and that produces products of NO and products of Cl2. Then to run the math properly, all we have to do is remember that 2 of these will give me 2 of these and 1 of these, so that means 2 squared power. 2 of these will give me a 2 here, and then 1 of these means I'm just going to leave that as 1. So very important step to convert these into the exponents so that the math will work, and we can depend on that 1.6 times 10 to the negative 5 to bring us home in terms of any unknown quantity. Now, if this time around, well, you know, anybody have a 2-liter bottle of soda? Okay, let's just call this a 2-liter chamber and call it even. So let's say this time around we inject some NoCl in a 2-liter chamber, and the amount that we're injecting in the 2-liter chamber is exactly 1 mole. right? So if we inject 1 mole of NaCl in a 2-liter chamber, what will the equilibrium be of all three? What will the equilibrium concentrations be of all three after it reacts and reaches equilibrium? So 1 mole of this guy will actually give us a concentration of 0.5 molar because we're in a chamber something other than the size of 1 liter. So we do have to convert that to the actual concentration this time around. So initially, the amount of this that we have is 0.5 molar, and the amount that we have of this is 0, and the amount of this that we have is 0, because it's initial, and none of it's reacted yet. We inject a 0.5 molar in at the very beginning, so it hasn't had a chance to convert over, so the raw numbers of each that we start with are 0.5, 0, and 0, then it reacts, and then after that reaction hits equilibrium, we could then say, well, what could we say? Again, the tip is you can make X anything that you want, but the lowest value of X, if you can keep that to equal exactly 1X, then that's going to really make your algebra run simpler. So in this case, the amount of Cl2 that we produce, we could say, would be an unknown X value at equilibrium, and that would be based on every X of Cl2 that we produce would be based on every amount of NO that we lose in a quantity of 2X, and every NO quantity that we also produce in the quantity of 2X, and that's all based on the fact that they all came from this reactant, which is NaCl, and for every 2 NaCl's we lose, we produce 2 moles of NO and 1 mole of Cl. So if we keep it all in that X language to correspond with our balanced equation, then we could say that at equilibrium, we'll have our 0.5 molar minus 2X, and our NO amount will be just simply 2X, because we started out with 0. So at equilibrium, that's what we got, all right? Right. Now, giving this one because what we've got is such a small K value that the amount of NaCl that we lose is actually insignificant to the initial quantity of NaCl itself. But since the amount of NO and Cl we had in the beginning was 0, then any amount would be significant to those products. And what do I mean by that? If there were a billionaire walking down the street, the amount of money that billionaire had in the bank at that very second, based on the investments and the interest rates changing and the stock market fluctuating and all that stuff, if that billionaire were to take out a couple dollars out of his wallet and give it to a couple of needy people, then if those people, when they started out that morning, had 0, they had nothing in their pocket and they're looking for money to buy a cup of coffee with or some food or something, then if they started with 0, a couple bucks to those people will be everything, because it will get them from 0 to a couple bucks, which they can then buy something with. But that billionaire handing out $2, if we ask that billionaire what was their exact net worth before he gave out the $2 and what was his exact net worth after, the $2 loss there would actually be insignificant compared to the net worth of that individual, all right? And that's because we are dealing with a K value that's so low that the transfer rate from reactants to products, it would be considered insignificant in the eyes of the NaCl reactant, because we're starting out with a decent quantity of 0.5 molar, and the amount of that 0.5 molar that we lose, we're going to find is going to be very tiny. So a lot of times instructors will cut off at a particular K value and say, hey, if you have something at around 10 to the negative 5, or even smaller than that, negative 6, negative 7, negative 8, then that'll be our insignificant cutoff point where we can not have to worry about that amount that we're losing. Or another rule of thumb, which I think is actually more used now, is like a 5% loss or transfer. So if it's less than 5% that's actually converting over, it would be considered insignificant enough to kind of ignore mathematically when we're doing the setup here. So what do we mean by that? Well, if we're doing the math setup here, we are going to say, and I'll plug the numbers into here, right? Because this equation's already set up. So how much NOCl should we have at equilibrium? Well, according to this, it should be 0.5 minus the 2x that we're losing of NOCl. So I'll just plug the number in. So 0.5 molar minus 2x. And that would be squared, of course. How much of these guys are we talking? Well, we don't know. We don't know anything about that because we started with 0 and we're just producing some amount. But comparatively, we're going to produce 2x of that, and comparatively, we're going to produce x amount of that. So that's going to be the squared power, that's just going to be the 1, and then that's going to be squared down there. Right? Now, here's where the lack of significance can kind of come in to speed this process up. Because the amount of x that this guy is losing is so small, so insignificant compared to the whopping 0.5 molar concentration that he has, we can actually forget about it. All right? And what that does is that allows us, I've got the K value also written on the other side, so I'll just leave that there. That allows us to cut this out and then just basically square the 0.5 value down here in the denominator. So what we're going to have up here when we multiply these two together is, well, remember that when we have the exponent outside of the bracket, it distributes into both parties. So that's going to be 2 squared is 4, x squared is x squared, so that's going to be 4x squared, then times this other x, so that's going to be 4x cubed. So it's going to be 4x cubed over, now, a simplified, getting this guy out of there, we don't have to FOIL it, we don't have to do anything, 0.5 squared, because we got rid of the 2x there. And 0.5 squared is going to be 0.25. And what that's all going to equal is the 1.6 times 10 to the negative 5, because that's our K value. All right. So what can we do? We can multiply both sides by the 0.25. I'll put it in here. That gets rid of that. We can divide both sides by the 4. And that's going to basically leave us with x cubed equals, and if we got the 0.25 on the top and the 4 on the bottom, that would be like saying 1.6 times 10 to the negative 5 over 16. And what we could do is we could take the cube root of both sides. And when we do that, that gives us x equals 0.010. Right? So, because the 0.010 is a lot less than, in this case, 5%, we can, we can plug that back in if we wanted to, but quite honestly, it's going to break some significance rules there, so we wouldn't even be able to count on adjusting that properly, because we're, if we knew that this was out to 0.50000, then we might be able to debate that, but because we're less than the 5% and we're at a number that's 10 to the negative 5, then it's considered insignificant enough to count out. Right? So with all of that, we can say that that would be our quantity of Cl2 at equilibrium. 2 times that amount would be our now known quantity, which is now going to be 0.020 amount of NO, and then for all practical purposes, the amount of NOCl that we have is going to be, still around 0.5, because NOCl is kind of the billionaire, and the amount that it's losing is peanuts. But since these guys started at 0, then every little bit helps, and that means everything to them, right? So there's a case where we are able to, take a shortcut because we've got some insignificance there, right? And then finally, you might have some questions where they're heterogeneous, meaning, because in this case, whether I write them or not, we've been dealing with everything that's a gas at this point. So it's a gas. So, you could get a case where, I said this was the last one, didn't I? But this is really the last one. You could get a case where you're reacting H2O, actually as a gas, as steam, with solid carbon, and that's producing hydrogen gas and carbon monoxide gas. And in that case, what are our reactants? Boom, boom. What are our products? Boom, boom, right? So the H2O concentration will go on the bottom, whatever that is. The carbon concentration will go on the bottom, and the H2 gas will go on top, and the carbon monoxide gas will go up on top. But these three are all gases. This guy's a solid, and if something is solid or liquid, it doesn't go into the true mathematical comparative gaseous concentrations floating around in this sealed container. So it's actually wiped from the equation. So you would recognize it in the equation as the reactants and the products. But if one of these were solid or liquid, like this guy is, by the time it got to the math problem to work out to whatever its desired K value is, it's one less thing that we actually have to mathematically put into the equation and solve for. Other things that you can apply equilibrium to, this is dealing with molar concentrations in closed chambers with gaseous reactants and products. But comparative pressures are also used to solve and check these K values. So it's a lot less frequent in a class to use the pressures than it is the concentrations, but nevertheless, the procedures work very, very similar. It's just that instead of comparing the concentrations on a ratio, so to speak, you're instead using the math to compare their partial pressures. And there's also ionic equilibrium in solution, which can use the same math concept to solve for the unknowns. So again, going back to the beginning, understanding the concept of equilibrium. It doesn't mean that the reaction has come to a stop. It means that it's continuing to go forward while the reverse is now running at an equal rate to produce the same amounts that you're producing in the forward direction. So even though it appears to be stopping, there's a lot of stuff still in motion, but our net results are not going to increase past that point, and we're not going to go to completion. And the K values will tell us how successful those reactions are and how close they get to completion or not close, as we saw in the case of the NOCl. So hopefully that helps. Hopefully.